All right, so we're talking chapter 7 thermodynamics, I think. Or they like to call it here, thermo number 1. I imagine there's a thermo number 2 coming after that. So really, this thermodynamics, we were kind of talking about the first law of thermodynamics, which involves energy. And when we talk about energy, oftentimes we talk about kind of two types of reactions. That's an exothermic reaction, and an exothermic reaction, heat and energy is released. So oftentimes we think of heat and energy as a product when it is a endothermic type of process. Kind of like we talked about when we did Le Chatelier's principle. Endothermic, on the other hand, is when heat and energy is absorbed. So heat and energy is more considered a reactant in that case, like it is being added in. Probably the most common way we sort of express that in chemical reactions is with our delta H values, which is our change in enthalpy. And our change in enthalpy is going to be a negative value if it is exothermic, and it will be a positive value if it's endothermic. So for most part, energy positive type numbers usually implies an endothermic type process. Negative numbers implies more of a exothermic process. We can actually calculate the delta H of a reaction by taking the delta H's of all the products divided by, not divided, but subtracted by the delta H's of our reactants. These are typically values that you can find in a table, which are sometimes referred to as the delta H of formation. And remember that when we do this, you do have to take into account the coefficients in the equation. So you do have to multiply the values you find in the table by those coefficients. And the idea here is, as we talked about, is state functions. And state functions, again, are things that aren't really determined by the path that you take. Really, there's kind of two important things, sort of where you begin and where you end for your final state and your initial state. And again, as we talked about in a chemical reaction, kind of your final state is your products, your initial state are your reactants. So that's why oftentimes we take our products minus our reactants to understand what is happening. We saw some energy diagrams. And again, if you have an energy diagram that looks something like this, reactants to products, and there's obviously energy here. Our reactants are higher in energy than our products. So in order for this to occur, energy has to be given off. And that would result in a negative delta H. And that is because if we take the difference in the energy here between our products and our reactants, that is our delta H for this particular reaction. And since the products are a lower number, that would be like a smaller number minus a larger number in terms of energy. And that is what's going to yield you your negative number there for an exothermic reaction. Opposite is true if you have more of an endothermic reaction. It'll look something maybe like this, where our reactants are lower in energy than our products to begin with. That means energy kind of has to be put in or absorbed. And again, if we take kind of our difference between our products and our reactants, that's going to be our delta H for this reaction. And in this particular case, our products are actually higher in energy than our reactants. So that's going to be kind of like a large number minus a small number. And that's going to yield us that positive value for delta H when we do that. Remember, the hill that the reactants really have to climb to get to the other side is what is known as the activation energy, or E of A. And that is the minimum amount of energy required for a reaction to take place. Thank you. And again, it's that hill, as you can see over here, that would be the activation hill there. That hill is really, in terms of kinetics, or what basically makes a reaction, say, fast or slow. If you have a really large activation energy, then typically your reaction can be slow because there's not going to be as many reactive molecules that have enough energy to get up and over to the other side. If you have a smaller activation energy hill, then there's probably a greater amount of reactants that have enough energy really to get to the other side. That usually would result in a faster reaction. That's also why when you increase the temperature of reactions, you usually increase the rate, because that gives a greater proportion of reactant molecules that now have enough energy basically to get up and over that hill to the other side. So that's what increases it. We could also add a catalyst, which finds an alternative pathway for that reaction to take place. And ultimately how it sort of speeds up the reaction in most cases is it actually lowers that activation energy or lowers the hill that the reactants has to climb to get to the other side. And again, that means that more reactants can get to the other side. We finished up, I think, talking about specific heat capacity. And specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And there's actually an equation that goes with it. Q is equal to ms delta T. Q is our heat or energy. And that typically has 1 unit of either joules or calories, which are common energy type units. By the way, the relationship between those two, 4.184 joules is equal to 1 lowercase calorie. M is mass, which is typically in grams here. Delta T, again, the importance of delta T, as we talked about last time, is, again, you always want to go final minus initial when you're calculating delta T. You just don't want to take the difference because the sign that you end up with for delta T is really important. This is actually, again, like I said before, one of the few sort of chemistry things that you could actually leave in Celsius and not convert to Kelvin. And that is because of the specific heat capacity that usually has 3 types of units associated with it: joules per gram per degree Celsius, or calories per gram per degree Celsius. So since our specific heat's usually in those units of degrees Celsius, we could leave our temperature there. And by the way, that is the definition of specific heat capacity, the amount of energy, like joules, needed to raise 1 gram of a substance by 1 degree Celsius. So again, that's basically what the definition of it is. Now, as we talked about before, this is typically positive number. So again, that delta T is really the place where we're going to either get a negative value or a positive value. And if we do end up with a negative value for Q, our heat, that usually means it's an exothermic process happening. And again, if you end up with a Q value that is positive, that's an endothermic process that is actually occurring. And again, the temperature reflection of what's happening. If somebody is absorbing energy, then we would expect to see their temperature rise as they gain that energy. And vice versa, if somebody is losing energy, we would expect to see their temperature basically cool down. Remember, heat flows from hot to cold, right? So the hot thing gets colder, colder guy kind of warms up and stuff like that. Specific heat of liquid water, right? Remember all that stuff I was supposed to say. 4.184 joules per gram per degree Celsius is the specific heat of liquid water, or 1 calorie per gram per degree Celsius. Also a reminder that if you happen to come across a problem involving specific heat, and especially with water, for example, you do want to make sure that you do look up the correct state of it. So that 4.184 is for liquid water, but if you were doing something like ice, or if you're doing something like steam, which is also water, the specific heat capacity is more like 2 joules per gram per degree Celsius, actually, for both of them. One's like 2.03, one's like 2. So it does change, obviously, with the substance. And again, the larger specific heat capacity, again, that means you got to put more energy in there just to see a 1 degree temperature change occur. So something with a smaller specific heat capacity, you don't have to put as much energy in there to see the temperature start to kind of change more. Any questions on any of that there? All right, we did an example last time. I think we left off here, so why don't we do this one? 294 joules of heat is transferred to 10 grams of silver at 25 degrees Celsius. What is the final temperature of the silver if the specific heat capacity is 0.24? Okay, so let's take a look. Obviously, we're using our specific heat here. Q is equal to ms delta T. Remember that the one with the single energy unit is actually Q, so that is 294. We have our mass of 10 grams. We have our initial temperature here of 25 degrees Celsius. And we have our specific heat capacity of 0.24 joules per gram per degree Celsius. All right, so, well, I'm just going to solve for maybe change in temperature here. So change in temperature, if we divide these guys to the other side, Q divided by ms, since I have those, Putting that in there, 294 joules divided by our mass, which is 10 grams, times our specific heat capacity there, joules per gram per degree Celsius. Joules are going to cancel, grams are going to cancel. When we divide that, temperature will come to the top here. 294 divided by 10 and divided by 0.24. Going to get us 122.5 degrees Celsius. That again is not our answer because that is equal to the change in temperature. And the change in temperature is always the final minus the initial. So in this case, 122.5 degrees Celsius equals our final temperature, which is what we're looking for, minus our initial, which is 25. We're going to add 25 that way. And that's going to give us 147.5 degrees Celsius equals our final temperature. If we're significant figurine, then, you know, maybe like 148, maybe it'll be somewhere in that ballpark there, I suppose. As technically this would go to two significant figures, which would give us a whole number, and then we're adding two whole numbers, takes us to a whole number, so somewhere in that ballpark would work, I guess. It does make sense since it went up the temperature here, and it's an endothermic process, obviously, as it absorbs that energy. So we should expect the temperature to go up. Question. All right, so what happens when we have heat being transferred from one object to the next? As we talked about, we sort of think of heat being transferred sort of perfectly, if you will, which means if somebody loses a certain amount of energy, somebody else will gain basically the exact same amount of energy. The only difference really is it's sort of exothermic for one and endothermic for the other. So the only difference really is the sign that happens. So for example, if I took a piece of metal here and I heated this thing up, much like you might do on Thursday, to say a temperature of about 95.5 degrees. And I have, let's just say, go 65 grams of it. And let's say I have some water over here. And I got about 125 grams of water at a temperature of 25.0 degrees Celsius. I throw this hot piece of metal into my water here. Heat is going to transfer which way here? From the metal to the water, or the water to the metal? Yeah, the metal's much hotter, so it's going to release that energy right to my water. Probably would see our water's temperature here increase a little bit, about 27.5 degrees Celsius. Wow. Now, with that piece of metal sitting in my water, it'll eventually come to equilibrium, right, with the temperature of the water. And in this particular case, that means that the actual final temperature of our metal will actually end up being 27.5 degrees Celsius, as it's basically sitting in that water right there, and it'll come basically to the same temperature. Now, let's just say for our metal here, we wanted to figure out what is the specific heat capacity of our metal. We could do that, and much of what we do a lot in chemistry here is we kind of just look at water because we know a lot about water. For example, we know the specific heat of water, 4.184 joules per gram per degree Celsius. So if we think about the water in this particular case, we could actually use our specific heat equation for just the water. And what this is going to do is allow us to figure out basically how much energy the water is going to absorb from that hot piece of metal that went for a swim on a very hot day, right? So that is 125. That's like 125. 125 grams there, specific heat capacity 4.184 joules per gram per degree Celsius. Again, here we're going to go final temperature, which is 27.5 minus 25 degrees Celsius. See how bad I did with my made up numbers here. Not too bad here. can get us something like 1307.5 joules as our degrees Celsius, and our grams should cancel each other out in this case. Now, all of that energy that basically was absorbed by the water, and we know it's absorbed by the water because our Q here is positive, so it's endothermic for the water. All that energy had to come basically from the piece of metal that we dropped in there. So that means that by calculating the amount of energy that water gained, what we're able to actually figure out is how much energy the metal lost, because it all had to be lost somewhere and it went to the water. The deal though is, right, it is not an endothermic process for the metal, it's actually a exothermic process. So there is a relationship when you do something like this, that the Q of the metal is equal to negative Q of the water, which means instead of absorbing 1307 joules of energy, the water pretty much gave away 1307.5 joules of energy that is negative. So by figuring out what happened with the water, we're able to kind of back figure out what happened with the metal. And now if we look at the metal and go into our specific heat equation for the metal, ms delta T, we could solve for S, which would be Q divided by M delta T, taking both of these guys and obviously dividing it over to the other side. We're going to put in our number here, which is negative 1307.5 joules. Kind of like kilojoules, but not so much. Our mass of our metal, which is 65 grams. And now it's again really important here that we do final minus initial here. And again, the metal basically cooled down and its final temperature is actually lower than its initial temperature. And that's really important because that is going to give us what type of number here? It's going to end up as a negative number. And that negative, along with this negative, will turn our specific heat capacity back into a positive number, which is what it should be. And here we go, 65 divided by 27.5 minus 5.5. That is going to give us a specific heat capacity for our metal of 0.295 and 0.30 joules per gram per degree Celsius, as none of that cancels out basically in this particular case. Question on that. So that is a very, very common sort of way that we do it in calorimetry. You could actually do this very simply with a calorimeter. That's basically just a couple coffee cups, styrofoam coffee cups with a lid, and a thermometer is pretty much all you need, and you can do that. By the way, when you do this, as we'll talk about, if you do this at constant pressure, when you calculate Q, it actually equals the delta H of that reaction. So by just a thermometer, some water, you can actually figure out the delta H of a reaction by following really the change of what's going on with the temperature basically of the water. Question is all out there. All right. Why don't you try one here? 110 gram sample of metal at 55.5 raises the temperature of 150 milliliters of water from 23 to 25.5. I would say, to answer your question, so let's talk about it here. So in this case, we basically have the same situation that's happening as we were just discussing. We basically have some water and we have a piece of metal and we're going to dump the metal basically into this water. So we have kind of two categories of stuff that we have. We have information about our metal, which has a mass here of 110 grams. We do have the initial temperature there, I think, of the metal at 55.5 degrees Celsius. Now, in terms of the water, we have not the mass, but we do have 150 milliliters, which is our volume. We do have an initial temperature of 23 degrees Celsius and a final temperature of 25.5 degrees Celsius. As we just talked about, as soon as that metal goes for a little swim in there, it'll eventually obviously come to the same temperature as our water. So we really do actually know the final temperature here of our metal, which should be the same as it is in the water in that particular case. We always have the specific heat capacity for liquid water and other versions of water available to us. Here we are looking for S. In order to find S for the metal, we actually need to find our Q, and we're going to do that using water. Now, we have everything we need for Q except that we do have volume and not the mass of the water. So I would say in most cases, unless otherwise specified in a problem, you could use the density of water that you probably remember. That is 1 gram per milliliter is usually a pretty safe bet. Again, unless they specifically tell you like, hey, it's at some other degree and this is the density to use. Now, with that being said, obviously we would then be able to convert our milliliters using the density of liquid water. And again, 1 usually is a pretty good number to use in most cases. And that will give us 150 grams of water, which is obviously what we need here to do our calculation. But yeah, if they don't specify anything about density other than, our temperature, then you can use the density usually as 1 gram per mil. Technically, if they give you a temperature, I would say even most books would probably still use 1, unless they specifically say it. But you are correct, it does change with temperature. So we can now do our Q for our water, and we'll go with our 150 grams. We'll use our specific heat here of liquid water. And again, we're going to go final temperature, which is 25.5 minus initial 23 degrees Celsius. Everybody's going to cancel out except for joules, which is good. And that's going to get us here about 1,569 joules of energy. Again, in this case, our water is lower in temperature initially than our metal. So the water is going to be on the receiving end of all that energy. And again, we do end up here with a positive value for our Q. We then can now use our Q of our metal will be equal minus Q of the water. Which means the Q of the metal will be negative 1,569 joules, as it will be exothermic for the metal. With that, we now have everything we need to solve for our metal using the same specific heat equation, maybe with an M in there. And S here of our metal would be Q of our metal divided by M delta T. Taking our Q, again, the negative version here. Our mass of our metal, which was 110 grams. And again, here we do want to go final minus initial, get our negative that we need to get rid of the other negative. So that's going to be 25.5 minus 55.5 degrees Celsius there. Try to squeeze it in. And popping that into our calculator, 1569 divided by 110 divided by basically 30. Going to get us a specific heat capacity of 0.48. Again, none of the units cancel. Joules per gram per degree Celsius. Okay. Questions on any of that? You can also, which is what the other slide there that I wrote on, you can, because Q is equal to ms delta T for your water, and Q of the metal is also equal to ms delta T. You can set these parts equal to each other. ms delta T equals ms delta T. But the relationship is one of them has to be negative. Yeah, I got to distribute that negative into one of those. So you got to have that negative distributed on one side to make everything work out right. Because it should equal 0. And that's sort of what I scribbled all over on this page was there. So that's basically what this is saying. The overall heat should equal 0, which equals both of those guys together. But if you set these guys equal to each other, you got to distribute a negative basically on one of them. Otherwise, again, it won't come out correctly. Any questions on specific heat being transferred? Let's talk a little bit about energy and nutrition. I think we touched a little bit upon it the other day. A nutritional calorie is a capital C calorie, and one of the nutritional calories equals 1 kilocalorie, which is 1,000 of the little calories, lowercase c. A calorimeter is sometimes used to determine the number of calories in food. For example, this is what's sometimes referred to as a bomb calorimeter, and it is what it sounds like. It's basically a well-insulated chamber that has water in it. You put your chocolate chip cookie in there, got some wires and oxygen, you set your chocolate chip cookie on fire. And obviously it's going to release some heat to our water, and you can basically do a calculation like we've been doing. You can figure out how many nutritional calories is being released by that cookie that's burning there. And obviously convert that by just following the water's temperature in this particular case. Now, when we talk about food, food has three sort of caloric food types: carbohydrates, fats, and proteins. And each of those have what are referred to as a caloric value. So basically, carbs are 4 kilocalories per gram, bless you, and that's basically 4 nutritional calories. Protein also 4 kilocalories per gram, and fat is 9 kilocalories per gram. So that is how they, for example, calculate what's on your nutrition labels of all your food items, right? If you look at a nutrition label, it'll tell you how many grams of carbs there are, how many grams of protein, how many grams of fat, and you can actually just multiply each of these by that. So, you know, if you had something that has 5 grams of carbs and 2 grams of protein and 10 grams of fat, you basically can just multiply each of those by their caloric value. So 4 kilocalories per gram, 4 kilocalories per gram, and 9 kilocalories per gram. That's going to give me 20 kilocalories from carbs. That's going to give me 8 kilocalories from protein, and that's going to give me 90 kilocalories there from fat. You can add those all together, and that gives you something like 126 kilocalories, maybe. I don't know. I'm trying off the top of my head. And in this case here, probably went definitely the wrong way. I'm going to grab my calculator. I feel bad. I feel really bad about that addition there. It just didn't feel right to me. That 118. See, I went totally the wrong way. Unlike what you'll find on your nutrition labels, they typically round down for some odd reason. They typically like to round down when you do those things. All right, so that's like a 118 on a really better addition move there. And that would be how many nutritional calories there would be in whatever snack I just got there. Any questions about there? So as I mentioned before, we could do this very, very easily and figure out energy and chemical reactions by simply really just some coffee cups and a thermometer and a lid, and it works really well to insulate it. Now, we could do this like we've been talking about, like you throw like a hot piece of metal into water, like you're going to do, I think, on Thursday. But you could also do this with actual reactions as well. Most reactions involve solutions, and most solutions are aqueous, which basically means a water environment. So you can make a pretty good rough estimation of like the delta H for a reaction by just assuming specific heat of water for your reactants. And you can follow the change in temperatures occurring even if you mix like an acid and base together, or you threw some zinc in with some hydrochloric acid, did like a single replacement reaction. You actually, again, measure these things. And like I said before, if you do this at constant pressure, when you calculate that Q, that is really the delta H of a reaction, the change in enthalpy. And you could actually, for example, if you did like this reaction and you knew how many grams of zinc you started with, you could also convert that to moles and figure out how much energy you got per mole of like zinc that you reacted in that particular case. Any questions? The next we're going to talk about is the idea of what is known as Hess's Law. And Hess's Law is basically the idea of state functions. And it's that idea that it doesn't really matter the pathway you get there. Again, it matters kind of where you end up. And as you may know or may be familiar with, not all reactions occur in a one-step fashion. So for example, if we have this reaction here, this may actually be a result of a couple of steps that occur. Maybe we have A plus B goes to C plus D. Maybe there's a delta H for that. And maybe we got C plus D goes to E plus F, and maybe we got a delta H for that guy, right? And in this case, we can add these together. And again, anything on opposite sides of the arrow that are the same can cancel out or reduce down. And that gives us our overall reaction that we're actually looking for. If I wanted to calculate the delta H of this reaction, the delta H of this reaction would equal basically just adding the delta H's from each of the steps together in this case. And that will give us our overall delta H in this reaction. A reminder that if you do a couple of things to these reactions, the delta H's do change depending on what you do. So if you had a reaction like this guy here, where the delta H is 10, and you needed the reverse reaction, a reminder that the sign of the delta H will change. Now it will be minus 10 kilojoules if you want. Also, if you needed to, for example, multiply this guy by a common number, like 2A plus 2B goes to 2C plus 2D, for the delta H, what you do is you multiply that also by that number, and that would give you 20 kilojoules in this particular case. And the last thing that you could do is you might need to divide by a common number. So say we started with this guy, and we want to divide everybody here by 2, that would actually put us back up here to this reaction up on top, and the delta H would get then divided by 2 as well. So you need to multiply a reaction that has a delta H value by a common number. You need to multiply the delta H by that common number. If you need to divide by a common number, you divide the delta H. And if you need to reverse a reaction, the sign of the delta H changes, and that's because it's products minus reactants. So when you reverse it, your products become your reactants become your products. So in this particular case, if we were to add these together, these two reactions here, we get H plus plus a half of O2 gives us H2O. And if we wanted the delta H for that reaction, again, in this case, we're just going to add these two reactions together. We didn't do anything to it in terms of changing anything on either of those reactions. So for example, here, if we wanted to create this reaction here, and let's say we want, all right, let's say we wanted to do, let's flip it around a little bit. So let's say we wanted to figure out the delta H of this reaction, and we want to do so by using these two reactions here. So the idea here is we want to manipulate these two equations so that when we add them together, we basically end up with that reaction up there on the right. So the easiest approach really is to just try to get everybody on the correct side of the arrow and make sure you have the right amount of everybody. So for example, the first thing I would look at here is I see CO2, and CO2 is on the left-hand side of the arrow, and over here, that's where CO2 is, and it's on the right-hand side of the arrow. So I do know I need to reverse that reaction. In addition to reversing the reaction, I don't need one CO2, but I actually need 2 of them. So for this guy, I really need to reverse it and multiply that reaction by 2. So I'm going to do that. So I'm going to reverse it here. CO2 gives me CO plus a half of O2. And when I do that, the delta H of that number is now going to be positive 283 kilojoules. I then want to multiply this whole thing by 2, and that's going to give me 2 CO2, 2 CO, plus an O2 in that case. And that's going to give me a delta H of 2 times positive 283 kilojoules. So that's basically everything I need to do with that guy. The next one I'm gonna look at is O2 here. And O2 is on the right-hand side, but obviously here where I have the O2 and also the carbon is on the right-hand side, and I have the carbon on the left-hand side. So I know I need to reverse the top one to get everybody to the correct side. And I also need to multiply this guy by 2 as well in this case. So that's what I'm going to do. I'm going to reverse the top one and multiply by 2. That's going to give me 2CO, gives me 2C plus O2. Again, I reverse the top one, which means the sign now becomes positive 110 kilojoules. And I also multiply by 2, which means I need to multiply that by 2 as well. If I did this correctly, I should end up with the equation I'm looking for, which means that 2 COs and those 2 COs should cancel out. And that's going to leave me 2 CO2 on the left goes to 2C plus 1 and 2 of those guys. 2O2. Hey, that's not bad, actually. Didn't screw that up too bad. Now, in order to get the delta H for this reaction, we're just going to basically add up our modified delta H's for our individual guys. So that's going to be a 2 times 283 plus a 200, right? And that's going to give us here basically 766 kilojoules of energy. Question there. This reaction is exothermic or endothermic? This would be endothermic. Our delta H here is positive in this case. So that's really what Hess's law is. You basically are using a bunch of little equations, kind of moving them around and adjusting them so that when you add them all together, what you're left with is your desired equation. Any questions? Yeah.
Is it 110 or 100
What's that?
for the KJ?
Well, it might be 110,
Okay.
you know. I mean, if we're gonna be picky about numbers, so a slight adjustment here. That's a 220. Chemistry wasn't my thing. All right, so 786. This looks like I wrote it bad, like normal. So that's 786 there. We'll just cut all that out later on in the video. It'll be all right. That's it. All right, so still endothermic here, 786. Other questions? All right, why don't you try this one here, see what you end up with. Okay, so let's take a look. So again, the idea is just to build from these two, this equation. And again, my approach usually is just to try to get everybody on the correct side. So I see SO2 on the left, here I see it on the right. That tells me I probably should reverse that reaction. So let's do that. SO2 then to S plus O2. When I reverse that reaction, my sign of my delta H is going to change. So it'll go from negative to positive in this case. The next thing I got going on, I'll take a look at the SO3. The SO3 is on the right-hand side, which it is here, but we actually only need one SO3 and we have 2 here. That means we do need to perhaps just divide everybody here by 2. And if we do that, that's going to give me an S plus a 3/2O2, gives me an SO3. Again, here, I also will need to divide my delta H by 2 as well. And that's going to get me a 792 divided by 2. Looks like a 396. And this one is going to be negative since we did not reverse it or anything. At this point, then, if we did this correctly, we should add up to our equation we're looking for since we're out of equations. The S's will cancel. The O's will also reduce down, and basically that is 2/2, right? So that's going to leave us a 1/2 over here, right? O2. So that will get us our SO2 plus 1/2O2 goes to SO3, which is what we're looking for. Our delta H of that reaction is going to be basically adding these guys together. And that looks like maybe a 99, I think. Yeah. Minus 99 kilojoules. Question on that. So the key is just kind of keep track of what you did to each equation, how that affects the delta H, And again, you basically just add up all the delta H's together. Questions on Hess's law. So heat, as we talked about, again, can be defined as that flow of energy difference due to a temperature difference, and that transfer of thermal energy between two bodies that are different. The internal energy is equal to Q plus W. Q is heat, W is work. And the internal energy works kind of the same way. If it's negative, it's sort of like an exothermic energy being given off, and if positive, sort of being absorbed. Energy can be used, obviously, to do some type of work, right? Either on a system or by a system, on the surroundings. By convention, again, if work is added to the system, is positive, but if we remove it, it is negative. And one of the driving forces for reactions and sort of spontaneity is the spread of energy. And that's one of the things that makes a reaction, as we'll talk about, either be maybe spontaneous or non-spontaneous. One of the key elements to that, in addition to sort of matter spreading, is the spread of energy as well. So the spread of energy, spread of matter is really important for us determining whether or not a reaction is going to be spontaneous. Well, I'm going to go part 2 on this one. Why not? Even though it's really not. You should have done part 1 last semester, but they don't do that anymore here. So, you know, it's the only school where they don't teach that in the first semester. All right, now going back in order here, I think we're back up to 16, and we're going to talk about really the rest of thermodynamics. And we're going to get into some, I can't believe it, some different letters other than K. So we're going to talk about entropy, which is S. We're going to talk about Gibbs free energy, which is G. But of course, it wouldn't be this class if we didn't tie K back into it as well. So we will get back into our equilibrium constant there. So we're going to talk about really reactions and thermodynamics. And really, when we talk about thermodynamics, we oftentimes want to talk about whether or not a reaction is spontaneous. And sometimes people have a misunderstanding in terms of thermodynamics when we talk about a reaction being spontaneous. So sometimes people, when they hear the word spontaneous, they think you snap your fingers if I could, and the reaction happens really, really fast. And that is not what we're talking about here. When we're talking about spontaneous or even non-spontaneous in the sort of chapter or in thermodynamics in general, what we are talking about is under these conditions, would we expect this reaction basically to occur? And you can have a spontaneous reaction that is really fast. You could have a spontaneous reaction that is like super slow, and you can have anywhere in between. So when we talk about spontaneity or reaction being spontaneous, we're really not talking about how fast or slow the reaction is taking place. That actually is kinetics, where you deal with how fast or slow the reaction takes place. What we're dealing with is really just that question of, under these conditions, could be really fast, could wait all day, but will this reaction eventually occur? And again, it has nothing to do with speed. So sometimes books nowadays will not maybe talk a lot about spontaneity, but they will sometimes talk about this reaction is thermally product favored, or thermodynamically product favored, which means it's going to happen, or is thermodynamically reactant favored, it's not going to happen, basically. So I use personally spontaneous and non-spontaneous. Sometimes books these days will kind of swap out that for some other terminology, but the idea here is kind of the same. We're just trying to figure out, under these conditions, will this reaction happen? Again, it has really nothing to do with how fast or slow it's happening if we say it's spontaneous. Again, for example, ammonia is a spontaneous reaction, but if you do not use a catalyst, you'll be there all day waiting for that reaction to kind of take place. It's very, very slow. So again, it has nothing to do with that. So there are certain spontaneous physical processes and chemical processes that we know, hopefully. Water runs downhill. Usually it doesn't go up without some help, right? And that's also something that lends to spontaneity, is the idea of this reaction will occur spontaneous without any type of intervention. You don't have to do anything to it to have this reaction occur. Clearly, if you wanted water to go upwards, you got to intervene, right? Put a pump in there, right, to shoot the water up, right? It's just not going to happen by itself. Sugar will dissolve in hot coffee. Water freezes at 0 degrees and starts to melt above that. As we've been talking about, heat flows from hot to cold. A gas will expand in an evacuated bulb, and iron will really start to rust. All you need is a little bit of moisture and some oxygen, and it will basically rust. If you're skiing and you go down the hill, that's probably all you need to do is you're gonna go, right? If you go down the hill and start, you can't usually stop too much, right? That's gonna spontaneously happen. This is non-spontaneous, right? If you want to go uphill, right, you gotta put in some type of intervention there to help yourself up the hill. I'm assuming that is not what that guy wanted to see as he's coming down the hill, I imagine. You don't want to see something coming up in the other direction. Hopefully they kept a good distance from each other. If we have gas molecules over here separated by a valve, you see it on this screen, that's not bad. And if we open this valve spontaneously, right, these gas molecules are going to basically fill the other side, right? So that would spontaneously happen. If we started with gas molecules on each side, they are not going to just spontaneously decide to all vacation together and go to the left there without some outside intervention, like maybe a little bit of flame on that side or some heat to send them that way, right? So that is going to be a non-spontaneous sort of process. Now, one of the things we just finished talking about, which was enthalpy, and does a spontaneous reaction depend on a negative delta H, which is an exothermic reaction? So here are some examples, again, of some spontaneous reactions. We have a combustion reaction there, and that is negative 890, which is exothermic. We have sort of the formation of water from an acid-base reaction, negative 56. But we do have something like water, which is ice, will melt, right, spontaneously at 25 degrees there. If you take an ice cube out, it will start to melt to liquid water. That's actually an endothermic process. The dissolving of ammonium nitrate in some water, also an endothermic process, and that will happen as well. So what this shows us is just having a delta H that's negative and exothermic does not necessarily guarantee that your reaction will be spontaneous. You can have a negative delta H or an exothermic reaction that actually is non-spontaneous, and you can actually have a endothermic reaction that is also spontaneous as well and non-spontaneous as well. Exothermicity, or an exothermic reaction, is a good sort of starting point, if you will, or a good factor towards spontaneity. As we just talked about at the end of that last chapter, one of the things that help something be spontaneous is that kind of flow of energy, that kind of movement of energy out, in addition to the movement of matter as well. So having an exothermic type process is a really good point to moving towards a spontaneous reaction, but again, it will not necessarily guarantee it. So that means that we do need to look at maybe another thermodynamic value that will help us determine whether or not a reaction is going to be spontaneous. And that value is what is known as the entropy, not to be confused with our delta H, which, as we've just been talking about, is our enthalpy. This is delta S, which is our change in entropy. Entropy is the measure of randomness or disorder there is in a system. The more order that you have, the lower the entropy will be, and it actually will be more of a negative number, the delta S. So if you're doing something where it actually creates more order, less randomness and craziness, you actually will be moving the delta S closer to a more negative change that's happening. Now, if you are doing something where the amount of disorder, craziness increases, you are actually going to be moving the delta S into a more positive value. And that's a little bit different. Sometimes when we think about delta H, we think negative things happening. Here, the more crazy it is, the more positive you are. That is crazy. Yes. So it becomes more positive as you're doing that. So if your final entropy state is greater than your initial, then you will have a positive value and an increase in randomness. That also has a lot to do with, again, that energy spread and also the matter spread. So for example, you think about our poor ice cube that starts to melt spontaneously. In the liquid phase, there's a lot more water molecules being spread out. There's a lot more movement in the liquid phase than there is in the solid phase. There's a lot more disorder happening. Probably the easiest thing to think about is actually the change of states. In the solid state, everybody is packed in there pretty tight to one another. There's not a lot of room for movement, so things are very much ordered. There's not a lot of energy happening. As you go to the liquid state, things are still packed in there relatively tight to each other, but there definitely is a lot more energy and a lot more movement. That's why liquids are fluid, right? They can kind of move past each other, the molecules and stuff like that. And just by that process of moving around, there's a lot more disorder sort of happening in that process. And obviously, when we get to the gas phase, everybody completely breaks apart from one another. They're flying around crazily around the room, right? And there's a lot of disorder. That's how I remember it. How many things are flying in my face, right? This craziness that's going around and flying through your eyes there. So when we look at something in the solid state, it has a lot less entropy than something in the liquid state, and then in the gas state, it has a lot more entropy because there's a lot more craziness. Everybody's flying around, moving around, a lot of energy. Any questions on that? So again, our going from our ice to our liquid water, we would expect the entropy of that system to increase and become more positive, again, as it's melting. Obviously, as you would also go from liquid water to steam, that is basically gas molecules, right, flying around of water, and that would also increase in the entropy. Now, entropy is related and disorder is related to probability. And a probable event is one where there are many ways that it could happen. So for example, if we're in this room, there are multiple doors. There's probably a pretty probable chance that we could get out of this room if we needed to, right? You could choose any exit you want. It's not that grim of an example. The next example is more grim. Now, let's just say there are no doors and that's the only exit up there, that window, right? And maybe there's just one small window up there, right? Probably a little less probable that we all make it out of this room. See, I told you it was going to get worse, the example. You just have to be patient. So that is a less probable chance of happening. And something with a low probability of occurring will have a low entropy. Something that has a high probability of occurring, that would have a higher entropy, right? And one of the ways we look at probability is what is referred to as microstates. And microstates are different ways that you can sort of accomplish something. So we can look at these as molecules, or you could just look at it like a carnival game. I like to do the carnival example. I'm doing good on my analogies here today, I think. So let's just say we're trying to win the stuffed animal, right? And we got the big stuffed animal there at the carnival, right? And you go and you give the guy $5, $10. I don't know what it would cost these days. Probably more like $10 seems more reasonable. And they give you 4 balls, right? And they say, well, if you want to win the big stuffed animal, you need to get all 4 balls into one side of the compartments here. And we know that those balls are pretty juiced up, that they're just going to bounce out anyways when you toss them because maybe it's rigged. And so there's really only one way really that you could win that big stuffed animal is to get all 4 balls in one side. Technically, there's 2 ways. You could throw it on the other side, all 4 balls, but really one way you get that. So in this case, there's really only one way that you could do that. Now, let's just say, all right, well, maybe you don't want the big stuffed animal. You may want the medium-sized stuffed animal. So to do that, you got to get 3 on one side and 1 ball on one side. So there's 4 different ways that you could achieve that. And let's just say you want, to make somebody happy because you already spent all your money trying to win them the big stuffed animal and you want the keychain size stuffed animal, right? Just go home with something at this point. So they're like, well, fine, if you get like 2 on each side or, that's okay. And there's 6 ways you could toss the balls in there to get basically 2 on each side. The more probable event here, if you went to the carnival, is you're going to go home with the big stuffed animal or the keychain stuffed animal. Probably this keychain, right? Because all I gotta do is get 2 on one side, right? So because there's more opportunities and more ways you could achieve that, is probably a lot higher probability that you're gonna end up here. There's always that one that they give away, so they walk around with it in the carnival. So you think, oh, they want it. I'm gonna go give them all my money so I could try to win that as well. But there's only one way to do that guy, and that's gonna have a low entropy. This is the Boltzmann equation. This is the entropy. This is Boltzmann constant, which is on the bottom there, and natural log of W, which is our microstate. So just to illustrate this, obviously, if we're shooting for this guy here, and we take the natural log of 1, that is equal to 0, right? The natural log of 1 would equal 0, which means we basically have a very low entropy. If we took the natural log of 6 in this case, we do get a much larger number, like 1.79. And we would have a much higher positive entropy. So the take-home message is clearly there's a lot of ways to screw things up, but there's only one way to do it right? So that's the idea there. And so that's the idea here. If there's multiple ways you could do something, then there's a really good probability chance that it's going to occur, and it'll have a pretty high entropy, right? And if there's only one way to do something sort of correctly, there's maybe a lower probability of that occurring and a much lower entropy. Any questions on that? All right, well, I'm out of carnival analogies at this point. Let's stop. All right, so today is unknown day, I think, yes? Mix some things, get some colors.